In examples 20 and 21, we want to solve a given system of equations. Looking at the first two equations that we have in example 20, we can label those as equations 1 and 2, and then look at any restrictions on both x and y. In this case, x is the base of the logarithmic function. Whenever we have a log function, that base a had two restrictions on it, so those will apply here. X has to be greater than 0, and x can't be equal to 1. We also have restrictions on y. Since y is contained inside that log function, y has to be greater than 0, and 4y has to be greater than 0, which still just gives us y has to be greater than 0. So whatever values we come up with, both x and y have to be strictly positive, and x can't be equal to 1. In order to solve, what we'll do is use substitution by first taking equation 1 and rewriting it as an exponential equation, which would be x squared equals y. We'll take that result and substitute into our second equation. And then again use properties of logs to rewrite this as an exponential. This would become x to the fourth is equal to 4x squared. Subtracting that over to the left-hand side would give us x to the fourth minus 4x squared is equal to 0. And then we can factor out what's common, which in this case would be x squared, to get x squared times the quantity x squared minus 4 is equal to 0. Factoring one step further, we would get x squared times the quantity x minus 2 times x plus 2, which would give us three solutions, 0, 2, and negative 2. When we look back at those restrictions we set up though, x has to be greater than 0 and can't be equal to 1. So we throw out x equals 0 and negative 2, leaving us with only a single valid solution for x, which is x equals 2. We'll take that result and go back to equation 1, substituting in x is equal to 2. We'll get 2 squared is equal to y, or y is equal to 4, meaning our single xy coordinate pair that's a solution for this system would be x equals 2, y equals 4. In example 21, we can start off by labeling these as 1 and 2 again. And since we're taking the log of x and the log of y in different places, we know that x has to be greater than 0 and y has to be greater than 0. We can start off by rewriting equation 1 as the natural log of x is equal to the natural log of y to the fourth. Once those logarithms are exactly the same, we know that that means x equals y to the fourth power. And we can make that substitution into equation 2. So now we would have the log base 3 of y to the fourth is equal to 2 plus 2 log base 3 of y. We can subtract that 2 log base 3 of y to the left-hand side and then combine those logs to rewrite this as the log base 3 of y to the fourth. Let's go ahead and go back one step. I jumped just a little bit too far, too quick. So we'll subtract 2 log base 3 of y to the left-hand side, and we can go ahead and bring that 2 as an exponent for the y to rewrite this as the log base 3 of y squared is equal to 2. And then we can rewrite that as the log base 3 of y to the fourth over y squared by combining those two log statements. Or the log base 3 of y squared is equal to 2. Then we can use we can rewrite our log statement as an exponential by rewriting it as 3 squared is equal to y squared, or 9 is equal to y squared, and then take the square root of both sides to get y is going to be equal to plus or minus 3. However, we know from our restrictions that y has to be greater than 0. So our only valid solution in this case would be y is equal to positive 3. Taking that result, we can go back to equation 1 and substitute in this value of y equals 3 to get x is equal to 81, and our single xy coordinate pair that's a solution to this system will be the point 81, 3, or x equals 81, y equals 3.